Subsequently, an approximate models can be derived using some physical principles. And the challenge here is to find a new model that approximate the water wave equations with a high accuracy. And this will be the new extended KDV model. In the third part, we will analyze this model from the consistency point with respect to the Boussinesq system, and we gave the HSX solution with an order up to epsilon cube, and then we validate our theoretical result, and finally we give an application to Tsunami with a comparison with the previous or the old KDV model with the energy properties, in particular the mass and linear momentum equations. So ocean waves, due mostly to the wind, but also the gravitational force and the movement of the ocean floor, ocean water level will rise and fall in a complex and changing movement, transferring energy away from an area of disturbance. This transmission of energy occurs without the actual transportation or the change of the location. And also this transfer of energy along the ocean water is called ocean waves. So the theory of water waves is the main subject in coastal hydrodynamics and play a crucial role in applied mathematics and control theory. Looking out at the ocean, we often see a series of traveling waves called, we see often a series of waves called traveling waves because they transport energy but not mass. Predominantly, the transmission of energy occurs due to the wind blowing. So it creates friction between the particles of the wind and the water surface. In addition to the gravitational force and, of course, the movement of the ocean floor, or any kind of disturbance that facilitates the water wave formation. This disturbance reflects the wave characteristics from the amplitude to the wavelength, depends on the energy carried by. Now, the long ocean waves, such as tsunami or tidal waves, or any sources that reinforce the water wave formation, carry a huge amount of energy. So during their propagation in the mid-ocean, their shapes changes according to their either their position from deep or shallow related to the depth of the ocean. The second one is the bathymetric variation. And for example, in this case, if we have a slope in the bottom, in this case, the ocean wave speed will slow down and its height will increase fast. And finally, as we mentioned before, due to the air friction by the wind. Now, Leonard Euler derived the water wave equations using some physical principles like incompressibility, and the speed and the rotationality. And here, because these water wave equations are very complicated to be studied from the theoretical and numerical part, some simpler models can be derived here, such as the shallow water models, like the KDV or the Boussinesq system, or the BVM or Green-Nagy also. So in order to derive this system, we consider first a domain of water here. Domain omega t depends on time t. It's a variable domain, bounded above by a free surface and below by a flat bottom. We denote here by zeta to be the free surface elevation and zeta to be the outward unit normal vector. And here, the air resistance is neglected, so the only force applied to this system is the gravitational force. Now, this system can be seen in unidirectional or two-directional. Okay, that means that the domain can be expressed as two-dimensional case or three-dimensional case space. Okay, so this system requires some basic assumptions, like we mentioned before: the incompressibility, the homogeneity of the fluid, the rotationality. Also, we suppose that also at the boundary condition that the particles neither cross the free surface nor the bottom. And finally, we assume that this wave is zero at infinity. Actually, the first two assumptions means that the fluid is governed by incompressible Euler equation. A5 and A6 are actually the kinematic boundary condition, while A4 is the dynamic boundary condition. So we can translate this assumption into this system of mathematical equation. As we can see here, we have four unknown functions: zeta on a fixed domain, and the velocity vector v of three components on a variable domain omega t. So we aim now to reduce the number of equations and the number of unknowns of this system. And this can be done by using the potential theory. So due to the rotationality of the fluid, we can find a scalar function. We call it here phi, such that v equal to gradient phi. We substitute this relation into our system, and we get the Bernoulli formulation. And now we have, instead of four unknown functions, we have two unknown functions, the same as before, zeta on a fixed domain. And we have now phi as a one unknown function, but on a variable domain omega t. So the problem still appears in the domain that depending on time. Our goal is to find now a new function. We will call it psi, instead of the function phi, which will be defined on a fixed domain. And this is the idea of Zakharov. He gives the definition of the trace of the velocity potential on the free surface defined by psi to be equal to the gradient of equal to pi at z equal to zeta. And from this psi and zeta, we can solve our system. We can look carefully to this Laplacian equation with this boundary condition. We can solve this system, and we show that there exists a unique phi. Okay, so by finding phi, we can again find the velocity vector v, and so we can find the pressure v, and we solved our problem. Now, Greg and Zulem, from this definition of trace of the velocity potential, they gave a new formulation of the water wave equation, in which all the unknowns now are defined on the free surface only, which they used the Dirichlet-Newman operator. And so we get now a new system, which is called Zakharov-Greg-Zulem system. And we have now two evaluation equations on a fixed domain of horizontal coordinates. And remark that here we don't have any parameter z. We eliminate the z coordinate. We need now to define the characteristic of the wave. So we denote by lambda to be the wavelength of the wave, a to be the amplitude, and h0 to be the still water depth. We shall non-dimensionalize our Zakharov-Greg-Zulem system in order to make an easier comment on the qualitative property of our solution. So we start first defining epsilon to be the ratio of the amplitude over the still water depth, and this will be called the non-linearity parameter. We also define the mu to be h0 over lambda squared, and this is the shallowness or the dispersion parameter. We need also to non-dimensionalize the following unknown functions and variables. And so we can write again the Zakharov-Greg-Solim system in the non-dimensional form. Now, because of the complexity of our system, scientists drove to derive simpler models using some physical principles, starting with the John Russell about the phenomenon of soliton and his report in 1844. Then Boussinesq gave the first mathematical equation of the water wave approximated model, characterized by a weakly nonlinear and weakly dispersive effects on the horizontal bottom. Then Korteweg and his student Jeffries rediscovered the same equation, but now with one direction, in a unidirectional motion, balancing also the nonlinearity and dispersion effects. And finally, we have the general situation actually for the approximate, for all these approximated model known by Green and Nagdi equations, and this is characterized by fully nonlinear and weakly dispersive models. So in order to derive the shell water models, we need two main ingredients. First, the depth average horizontal velocity, which is represented by integrating over the bottom. Sorry, over the depth. The second one is the asymptotical expansion of del x psi using only the assumption of shell water regime or scale. Now, from this model, we can derive all the other models like Boussinesq or KDV or any model, approximate model, depending on the physical scale chosen. So the first point means that we can write the average velocity at this relation to be 1 over 1 plus epsilon zeta integral of del x pi over the depth. Now, for the derivation of the Green-Nagdi, we need to use first, for the first equation, we need to use the Green identity and the Dirichlet-Newman operator. And with doing some computation using Leibniz rule, we get that 1 over mu of the Dirichlet-Newman operator at psi equal minus the partial derivative with respect to x of hu. And we substitute this relation into our first equation of Zakharov. If you remember this one, in the first equation of it. Okay, for the second point, we need to use the important assumption, which is the shallowness assumption, which means that we can find an approximate potential velocity that will be equal to the summation of finite number of functions multiplied by mu j. Using this relation, we substituted again in the Laplacian equation that we seen previously, and we get now a system of ODEs. And this system can be solved. For example, here, if we take j equal to 0, we can substitute, we get del z square of phi j equal to 0, and we can solve it. We get phi 0 equal to psi. This is the first scalar function we find. We can find as much as we want by repeating the same computation with this ODE system. But for our interest, we will find only until n equal to 2. Okay, now we have find phi 0, phi 1, and phi 2. We can write again the approximate velocity potential, and then we substitute it in the average velocity. And after some computation, we get the asymptotic expansion of del x psi. That's what we are looking for. So we have everything now. We just need to do some replacement in the Zakharov-Greg-Solim system, and we get our extended Green-Nagdi equation. I call it extended because we derived for a high order. degree-negative equation actually for n equal to 1, and here we derive it for n equal to 2. And this system is well posed by an article published with Samir Asrawi and the others. And also there's another approach to derive again this system by Matsuno 2016. So let's focus on our problem, the KDV equation. So the KDV equation in its simplest form can be written in this equation, number 6. So the solution of this equation play a crucial role in coastal engineering, and it represents the propagation of water wave with a small amplitude and long wavelength. And we consider also the extended Boussinesq system. Actually, we don't need to repeat all the derivation. We just take again the extended degree-negative equation, and we do just this one of the assumption. We assume that we have the long wave assumption. So we just need to balance epsilon and mu. And in this case, we get Boussinesq system. And of course, we can repeat again all the derivation for a higher dimension. This is in 1 dimension. Now, we move to the important point, the derivation of our new model. First of all...
Sorry, can you go back? Okay, here, what's the relation between these two equations? What?
Okay, I need these two equations in order to derive my new model. You can see a relation between these two. From Boussinesq system, this is a two direction. Propagates, the wave here propagates in 2 directions. If you do some calculation with the perturbation, you get the KDV equation in 1 direction. This is the same equation actually.
Okay.
There is a derivation.
Not completely.
It's not evident. Of course, it's not evident. You can go from the Boussinesq to the KDV under a specific assumption. So to derive our new model, I call it the extended KDV equation. For the sake of clarity, I assume that epsilon is exactly equal to mu. And this can be done in 3 steps. It's a very technical part here. It's based on some asymptotic relations. Okay. So we suppose first we have the U solves the equation number 8. So equation number 8 is actually, if you look carefully at the left-hand side, this is nothing but the original KDV equation by taking only alpha equal to 1/6. And we have our new terms on the right-hand side. So we aim now to find the parameters beta, gamma, and delta. So we start first by changing or using the asymptotic expansion here for ux, x, triple derivative to change it to xxt. And this is also called BBM trig. And for the other terms, I put it on the right-hand side, and I call it again ABC. Okay? So again, we have the same problem. We want to find ABC instead of beta, gamma, delta. So we need another equation in order to find this parameter. So we look for a smooth function V such that zeta equal to U plus epsilon V. U actually is nothing, is the solution of the extended equation, and zeta will be the solution of the Boussinesq system. So after some computation and making derivatives, we can find epsilon V is equal to this linear combination. And all we need to do now is, again, some derivation and substitution in the Boussinesq system, in the extended Boussinesq system here from the second equation, and we can find these parameters. It's all about calculation, but long calculation. So now we have our new extended KDV equation. At the leading order, if we look carefully to equation number 13, we get the transport equation. Okay? And again, if we eliminate the terms that multiplied by epsilon squared, we get the original KDV equation, and we have it. So what we do in this article, we recovered the terms that we call it in the previous, or they call it in the previous article, O epsilon squared. We recovered the terms, and that's why we call it this model is an extended KDV equation. And this new system is well posed, or actually locally well posed, for an S greater than or equal 5/2. And this is work was studied by Marwan Berjawi last year. So in order to study the properties of this model, first property is the consistency. So we need to give a definition of the consistency. We assume here epsilon to be very small and epsilon 0 to be a positive constant. And we say that any family of pure zeta, where zeta between 0 and epsilon 0, HS consistent on a time interval 0, t over epsilon, with respect to the Boussinesq or the extended Boussinesq system, if it satisfies the system with a remainder bounded in L infinity HS.
Why? Yeah, pure epsilon.
Where?
Yeah, the time here is t over epsilon.
Yeah, in order to guarantee that our model is well posed. This comes from the well posed. Okay, so from that.
Anyway, it's not a restriction because when epsilon equals to 0, you have infinity.
Yeah.
Okay.
So we may get the solution may get blow up in this case. So for the first proposition that we have done, we assumed again the same given we had before, and we take here for S large enough and T to be strictly positive. And for any family of solutions that solve the extended KDV model, we have the family of U zeta with the zeta defined by this formula. It will be an HS consistent with the Boussinesq system. And what do we mean by HS consistent with the Boussinesq system in the sense of the previous definition? Okay, for the proof, all we need to do is to use the definition, or to prove, depending on the definition. And this is easy to see. We just need to use this zeta and substitute it in the extended Boussinesq system for the first equation. And again, for the second equation, we're doing some computation. The next theorem serves in the construction of explicit solution of our new model. So remember that from the extended KDV equation, if we eliminate the terms that multiplied by epsilon squared, we get again the classical KDV equation. And this gives us a clue about the general solution of our new model, which will be this relation. U equal to U KDV plus epsilon squared V. And V here will be the solution of this linear transport equation with a known function up here in terms of the UKDV. So UKDV, I using this notation just for to denote the solution of the original KDV. And this U will be an HS consistent with our new extended KDV equation. The proof relies on this relation. So we have to do again the derivative with respect to time and x, and with some computation and using the relation of transport equation, we can easily get the result. This is our main theorem. That's about the HS explicit solution with a corrector of order epsilon 2. So we start first by taking epsilon to be the same order mu. UKDV, again, the solution of the original KDV equation. And I've defined, this is nothing, this is but the same notation of the previous stuff. And we need also to, we consider also an initial data, U0x equal to UKDV 0 plus epsilon squared V0. And then we have that the general solution of our model will be called an HSX solution with a corrector of order epsilon q. So in order to validate our theoretical result, we need, first we will define these residues, R infinity, R0, and R1 to be related to the norms L infinity, L2, and H1 respectively. And here, for this simulation, we compared the error, the residues, okay, for epsilon between 10 to the power minus 1 to 10 to the power minus 5 at a fixed time. And in comparison, we observed that our behavior of our graph is in agreement with our theoretical part.
Sorry, the question, what are you simulating? What equation you are approximating?
Okay, I'm simulating the residues, these.
Okay, now this one is
the residues. Okay, there's some simulation for the integral. If you look carefully about the solution here, we have an integral of sorry, I didn't clarify this part. U equal to UKDV plus epsilon squared V0 plus integral from 0 to t. Okay. And this is, we used here the numerical simulation for this part in order to find the residues.
So, first of all, you compute KDV equation.
Yeah.
The solution of KDV equation.
Yeah.
And then you inject here to compare with the residues of...
Exactly. Okay. And we substitute in the equation, and this is our...
So you are solving KDV.
Yeah, we are just validating the theoretical part in this at this point.
Okay.
From here,
is getting the solution of an extended system starting from an elementary equation using this formula, which is some kind of UML principle.
Yeah.
Okay, and
but you are not solving the modified equation. You are just solving the original KDV equation.
Because you can use the UML principle and the fact that it has epsilon in front of all the non-linearities. So he has x minus t because his transaction is method of characteristics somehow.
Okay.
And this means that our new model is considered as an or is the theoretical, sorry, the numerical results is in agreement with our theoretical part that we can see here. Okay, now we move to the interesting part, which is about the Tsunami model. So Tsunami is actually an oceanographical phenomenon characterized by its long wavelength and small amplitude. So several geological sources such as glacier, rock avalanches, volcanic eruption, and earthquakes facilitates for the enormous waterways. So the displaced water column originating by the impetus here creates or launches a train of waves carrying enormous amount of energy with a high speed. And during their propagation in the mid-ocean, or at the meantime, they leave the mid-ocean and start shallowing. So at this stage, the tsunami wave will slow down and the psi will increase fast, and the impact of hitting the environment or the coastal infrastructural triggered by tsunami runoff into the shore will be devastating. So actually, tsunami is about an earthquake. Okay, start from earthquake and then goes with this huge amount of energy. So we will apply our model to this tsunami waves. We consider again our model, but written now in the dimensional form. And we subjected to this initial data. And here A0 will be the amplitude, H0 the still water depth, and C0 will be the linear speed of water propagation. And the numerical scheme will be chosen here is called method of line. The method of line, or the essence of applying this method, is to transfer our physical problem into an ODE system, depends on time only. So our study will be focused on an initial value problem, depending on time only. And so the numerical solution can be solved with integration, with integrating this ODE system, because it depends on time. Okay, for the simulation, we used the ODE 45 built with MATLAB, and we considered the domain from 0 to 400 to get our long wavelength, and the time from 0 to 6. And we take the amplitude equal to 2 and the depth equal to 20. And in comparison, we observe that also we applied to this simulation the numerical part and the H-asymptotic solution to be compared together. So in comparison, we observe that the waves, the tsunami velocity waves, preserve their shapes during their propagation in the mid-ocean. And also, this graph exhibits that there is an agreement between the numerical and H-asymptotic solution with a very small error. Okay, so the question arises here: what are the optimizations that the extended model give us, and how much is accurate from the classical KDV equation? So to answer these two questions, we plot the solution of the extended model and the original one with the same initial data, and by taking epsilon, for example, equal to 0.1. And in comparison, we observe that the performance of our new extended KDV equation is superior, and with a very small error, the maximum error reached is about 0.014. So the second aspect that manifests the prediction of our new model is the conservative load. So first, we rewrite again the extended KDV equation in the conservative form, and the quantity here inside the time derivative represents the accumulation of the mass density, while the quantity inside the partial derivative with respect to x represents the mass flux through cross-sectional unit area of the water flow. And the second conservative law is the linear momentum, but here we calculated approximately up to order absolute truth, because our new model is no more integrable. Okay, so we need to find it approximately. And here, as we can see in the table, the integral of motion is invariant with respect to time for the KDV and the extended one. For the mass conservation, and for the momentum, as we can see here, we have a small error, and this is due to the integrability of our model. It's not more integrable, but we have improved the energy quantity by an order of epsilon squared. So what we have done in this presentation, we gave a rigorous derivation in the sense of consistency with the Boussinesq system and with our model with in the case of a flat bottom. We gave the HS explicit solution with a corrector of order absolute cube, and we gave also an application to Tsunami model to describe this phenomenon. And finally, we compare it with the old version, KDV, in particular the mass and the nominal. So what we look for in the next step is to study the case of the KDV equation with uneven bottom. And this is an important point because this study will enable us to study the effects of the coastal slopes of the tsunami run-up behavior near the shore. And the second problem is about the presence of the surface tension. Okay, actually now I am in my second year of PhD. I'm working now with Professor Roberto and Roberta Piantini with not a similar situation, it's a different situation. We are not working on the free surface. We go into, if you look carefully for this example, this is a part of the ocean. We are working with the internal waves now. So we consider here a stratified fluid. Stratified means that, for example, from this figure, as we can see that when we go deep in the ocean, the density will increase. Sorry. And this is what we mean by stable or stably stratified fluid. So this is an important assumption we needed to study the problem of the large time well-postness of this model. And this model, what's make it different is the presence of the viscosity term in the velocity equation. And the method will be used to solve this system will be the classical energy method and using the Brich and the Desjardins kappa entropy. Okay. The second article that I'm working on is a coupled system of two KDV equation. And what's the physical meaning of the second problem? If we look carefully again to this figure, we have this zone called a picnic line zone. Actually, this is the layer between the shallow layer and the deep layer. And during this picnic line zone, it witnesses a rapid increase with respect to the density. So we are interested to take here two internal long waves with the different modes and to study the exponential stability of this model subjected to a boundary condition. Actually, without the boundary condition, this model is well posed on R, but the problem becomes more complicated when we try to study it on the left Dirichlet boundary condition. And this is still open problem, to study the well postness of this system. And the second goal, of course, to study the exponential stability, which means that the energy of this system will decay exponentially to the equilibrium position. And so the method will be used here. It's called the backstabbing method. We aim to build a control, feedback control, which will give us this result. And the second goal here is to design an observer, and so we can show our work with the simulation. And that's all.
Thank you very much. Is there any question or comment?
I have two questions. Okay. First of all, thank you for your presentation. The first one is more, let's say, a curiosity. When you study the propagation of the Tsunami.
Okay.
We use the solution from the KDV equation.
Yeah.
This is generally a leading order solution. Did you try to compare, for example, the behavior of your new system in comparison to higher order solutions? I'm thinking about there are some solutions obtained by perturbation expansion from Fenton to the ninth order for solitons, which are considered practically exact solutions. So to understand how much your model increased the propagation, estimation of the propagation velocity of this tsunami, the shape, the maximum height, this one.
Actually, because this is a new model, we just simulate the layer in the mid ocean. We didn't go to the shallow water because in the shallow part you need to know to understand the bottom of our ocean. So we need to study again the derivation with the existence of the bottom, and so we can describe the completely all the stages of the tsunami. Yeah.
But okay, the second question was actually on shallow water agency, because I work on this program. Just curiosity in this case to understand if it was possible to modify the equation to account for the propagation towards the shoreline. The description, for example, showing effects on a planar beach, on the wet-dry movement of the interface, like, for example, in a sort of nonlinear shallow water equation model. So according to me, is it possible to find a real shallow water approximation of your system, which can be regarded as an enhancement of nonlinear shallow water equation, for example?
Yeah, but we need to develop our model more into the next step, because here we just studied for a flat bottom, so we can't understand the behavior of the wave near the shore like that. But for example, if you can study the tsunami using the KDV model, you can study everything you want because we have this model proved, just fully justified with a variable model. But the accuracy will be less than this one.
Okay, I see a curiosity. But what's the difficulty to study an even bottom when they were not flat?
We could have some terms. Of course, the first one is the world postness our model. I think yes, we can do it. We can do it. We can repeat the same derivation, but with the existence of this term, the bathymetric variation. For example, with the classical KDV, the bathymetric variation occurs here, near this fraction. Yeah. So with the existence of this term, we can.
If you know the topography, you can inject inside.
Of course. The topography is important to describe fully how the wave behaves near the shore or in the shallow or at any point. And of course, we expect that in the shallow it will be very high with the low speed.
Okay.
But I choose this model, I choose this phenomenon actually because it's the most appropriate. If you compare it with the other models, I think you can find this property of the small amplitude and long wave. They have the same characterization for the tsunami and for the KDV. They both characterized by a small amplitude and long wave. So that's why I chose the KDV equation to represent this phenomenon.
It is a little bit difficult because when you have a bottom which is strongly varying, obviously the wavelength is going to shrink, and the amplitude is going to grow. So you go massively out of the range of the validity of KDV.
So you have to come back to Euler equation. Or
KDV
for
is
Greenland.
okay for a tsunami, which is very, very far away from the houses.
Yeah.
When it goes near the houses, usually the KDV approximation is quite poor because you go completely out of the range of the applicability.
Yeah. Anyway, there is a book.
You begin to have a lot of optimization.
But
There is a book.
it's a sort of contradiction in the philosophy because generally through these models, because I worked on these models. From one side, when you are on flat bottom on a certain reference depth, then small bottom variation, the idea is to increase the description of dispersion effects. And this leads to, for example, higher order terms, which are higher order derivatives and so on, which when you go to shallow water condition generates a lot of problems because as you know, you are out of your hypothesis and you have a lot of oscillation because this terms becomes the relevant terms in comparison to the leading. So on the other side, you may think, okay, I have to go back to the earlier equation, but this is not a good choice because the earlier equation, when you have an interface, a moving interface with the wet-dry interface moving up, and are a problem. So the contradiction is that you have to go back to the nonlinear shallow water equation, which are actually an hyperbolic, the simplest hyperbolic system or linear system for shallow water equation, which are no dispersion. And so in this case, they have not this problem of oscillation clause, for example.
You have
shock dispersion.
No, you have shocks.
You may model shocks, which can be done in shallow water with strong theory behind.
But the non-linear shallow water is only of order 1. And here deriving without.
Yes, but in this case, you cannot use anything else. Let's say anything else, not true, but however, they are the strongest model for this propagation really shallow condition. Then the problem is how to match this, to have a model which can go from, let's say, intermediate deep water condition up to the shoreline. So this was my question before, because sometimes you need something which can cover the distance between this reference flat bottom and the shoreline. And this is the real great problem of propagation model for waves.
Most of the time you have the deep waters.
Yes.
Yeah, and just for the
To hit.
Yeah. It's a good model.
Yeah.
If you need the
Yeah, there is a book for I think Adrian Constantine or like that. He talked about tsunami, and finally he tried to explain why the KDV has these nice properties to be chosen to describe this tsunami propagation. I mean, there are some references also for.
No, during the time your wave looks like a river. The KDV basically the river, right? No, there is a story of a guy on a horse.
Yeah. This is
right?
John Russell.
Yeah. So basically, the point of the equation is to be able to let solitons interfere with each other. So this goes very well in the sea. The bottom is very, very deep, right? But as soon as the bottom goes up, then you begin to high frequencies, and we are not sure anymore that everything. I mean, solitons can cross without interfering, etc. So I think that when you go very close to the shore on the tsunami model, the system which supports solitons is perhaps not, it does not describe exactly the dynamics. The little that I understand,
yes, it's difficult to actually to do a correct modeling of the dispersion. That is the problem, actually.
Do you think you have a lot of dispersion when you are close to the shore?
It's not the dispersion. The fact that distance becomes not negligible because of they are made in this approximation higher the derivatives. So they cannot be controlled. They give oscillations.
Absolutely. Yeah, absolutely. Because if you cut all these terms, what you get is something like the conservation law, and the conservation law gives you a shock. So basically, you have these dispersive terms which regularize between a lot of poles, which regularize this shock by making oscillations. But you don't know if these oscillations